359 meters above a Himalayan river, 1 millimeter of error would have sent 10,000 tons of steel into the gorge.
At this height, a drop bolt takes 11 seconds to reach the river keeping, and there are 306,000 bolts holding this bridge together.
In 2004, this was a vertical cliff face accessible only by mule. No road, no foundation.
Before a single foundation could be poured, engineers had to build 4 kilometers of road into a cliff face that had defeated every previous attempt.
20 years, 28,000 tons of steel, and 66,000 cubic meters of concrete.
The buckle foundation alone required excavating 1 million cubic meters of unstable Himalayan dolomite from a slope angled at 60 degrees.
Each 33-meter anchor penetrates through fractured dolomite into competent bedrock, preventing the cliff face from shearing during the 60-year construction window.
The S40 foundation excavation descends 47 meters into the mountainside, deep enough to anchor. Each foundation requires a reinforcement cage weighing over 200 tons, hand-tied by specialist steel fixers working in cells of 8.
Every structural component had to navigate 4 kilometers of cliff-edge switchbacks, where a single miscalculation would send 20 tons over the edge.
200 tons of reinforcement steel now occupies the S40 excavation, waiting for 3,000 cubic meters of self-compacting concrete.
The first reinforcement section takes 40 minutes to position. Each tie wire must align within 10 millimeters of design coordinates.
Lower, hold!
Modular steel formwork capable of withstanding 50 kilonewtons per square meter encases the reinforcement, preparing for a continuous 72-hour concrete pour. Twin batching plants produce 120 cubic meters of self-compacting concrete per hour, feeding 3 boom pumps positioned at the excavation rim.
Self-compacting concrete flows around 300 tons of reinforcement without vibration, a continuous pour that will take 72 hours to complete.
800 cubic meters of concrete placed per shift, the foundation rises 12 meters through the night as exothermic heat turns the formwork to steam.
17,000 cubic meters of reinforced concrete cured for 28 days trade. The S40 foundation now weighs 42,000 tons and will anchor the western arch foot.
As the western foundation cures, the eastern excavation advances through quartzite and shale. 2 construction fronts. Laser survey equipment spans the gorge during the S50 pour, verifying alignment to within 3 millimeters as 3,000 cubic meters of concrete sets.
2 foundations containing 30,000 cubic meters of concrete now face each other across the deepest railway gorge.
2 purpose-built fabrication workshops, one on each bank, manufactured 31,000 tons of structural steel.
The world's largest crossbar cable crane required 2 steel towers, 127 meters on Kauri,
2 54mm suspension cables span 915 meters, installed by helicopter, and the first steel pier base rises 50 meters from assembly yard to foundation.
The base segment must align with 52 anchor bolts simultaneously at 360 meters above the river. Repositioning is not an option.
52 bolts torque to 4,800 Newton-meter, followed by non-shrink grout that transfers 40,000-ton arch loads into the foundation.
Under cranes. The cable crane travels 915 meters between construction fronts southward, delivering 35-ton segments to
131 meters of steel pier, 38 segments, 4,200 tons, rising from foundation level to the point where the arch will begin.
Each arch segment requires 480 hours of precision fabrication, curved to match the 407-meter span within 2 millimeters.
Every weld on every arch segment passes phased array ultrasonic testing, scanning 63mm plates for defects smaller than 1 millimeter.
Temporary stay cables extend from the pier top to anchor points above the foundation primer. Each cable supports the growing arch cantilever until closure at the crown.
In 3 weeks, 12 segments extend the western cantilever 132 meters into the void, and each stay cable straining against the growing weight.
2 arch cantilevers grow toward each other across 200 meters of vertical air, each segment installation reducing the gap toward the critical crown closure.
Each added segment redistributes 10,000 tons of force through the cantilever ganglia.
40-meter wand bracings connect the arch ribs at each panel point, installed from suspended platforms 300 meters above the river.
20 segments on each side twinned. 8,000 tons of steel suspended over the gorge. 2 cantilevers now just 27 meters apart.
Laser surveying spans 27 meters of void drawn, measuring the gap to within 3 millimeters before the critical crown closure segment is fabricated. The crown segment is fabricated to exact survey dimensions, 11.2 meters long, machined to close a gap that changes with temperature every hour.
The crown segment rises 300 meters toward the gap between 2 cantilevers. 8,000 tons of arch, waiting for the connection that completes the span.
5 millimeters thick, the maximum deviation allowed as the crown segment descends between 2 8,000-ton cantilevers built from opposite sides of the gorge.
Alignment pins engage on both sides simultaneously, completing a 407-meter arch that was built from 2 directions and meets within 2 millimeters.
The arch closes, but celebration lasts only seconds before 20 erectors begin installing
480 bolts stalked in star sequence over 6 hours to meet. Each connection verified to 4,200 Newton meters before load transfer.
Stay cables detention in sequence over 72 hours, transferring 8,000 tons of cantilever load into arch compression as designed. 10,600 tons of steel arch now self-supporting temp. All cantilever stays removed, the structure carrying its weight through pure compression.
Total bracing stiffened the piers against 266 km/h winds and Zone 5 seismic loading, the most severe design criteria in Indian railway history. Pier caps distribute deck loads into slender columns, each cap requiring 300 cubic meters of reinforced concrete and precision bearing alignment. 48 deck segments, each 24 meters long and 85 tons, fabricated with integral rail bearer supports for broad gauge loading.
85-ton deck segments rise from assembly area to track level thrown. The deck structure sitting 30 meters above the arch crown at mid-span.
280 bolts connect each deck segment splice. No field welding permitted, ensuring quality control matches workshop standards.
Vertical hangers transfer deck loads into the arch through 200mm pins. Each hanger machined to within 1/10 of a millimeter.
36 vertical hangers now connect deck to arch, distributing 15,000 tons of track structure into the arch compression ring.
A 150-meter launching gantry advances across approach piers Paime, positioning 120-ton deck segments at 4-day intervals.
Structural continuity across 1,315 meters, every deck joint bolted to create a single structural unit for train dynamics.
7,000 cubic meters of concrete fill the arch interior, adding mass for stability while protecting the steel core from corrosion for 100 years. Rail bearer pads position every 600 millimeters across 1,315 meters, isolating train vibration from the steel deck structure.
60-kilogram rail sections join into continuous welded track, thermit welding creating seamless rail across the full bridge length. Every rail weld ground to 3/10 of a millimeter tolerance, eliminating impact loads that would hammer the structure with every passing wheel. Check rails run inside the running rails across the full span town, a redundant safety system preventing derailment 360 meters above the river. Catenary masts rise every 50 meters, the bridge designed for 25 kilovolt electrification, though initial trains will run on diesel.
The cable crane that delivered 30,000 tons of steel now dismantles.
3-coat protective system covers every square meter of steel. 260 microns of corrosion protection for 100 years of Himalayan weather.
Aircraft warning lights flash from the arch crown, visible to pilots approaching Srinagar Airport 40 kilometers to the north.
Drainage channels direct 1.2 meters of annual precipitation and heavy snowfall away from the track, protecting the rail surface year-round.
Signaling systems integrate the bridge into the Udhampur-Srinagar-Baramulla rail link, axle counters and color light signals controlling train movements.
Ultrasonic anemometers monitor wind speed continuously. Trains halt automatically when conditions exceed 90 kilometers per hour.
Over 200 sensors monitor structural health continuously. Any deviation from baseline triggers immediate engineering review from the Delhi Control Center.
960 tons of loaded wagons assemble for static load testing tone. proving the structure to design limits before any passenger service begins. 960 tons rest at midspan, deflection measuring precisely 85 millimeters, exactly matching 20 years of engineering calculations. Dynamic testing increases from 30 to 100 kilometers per hour, verifying the structure responds within design limits at full operating speed. Laser scanners build a three-dimensional clearance map, verifying 300 millimeters minimum between the loading gauge and every structural element. Native vegetation returns to slopes disturbed by construction. Deodar cedar and blue pine restoring the Himalayan landscape around the bridge. Railway Board inspectors verify 20 years of engineering against final test results, signing the certification that clears the bridge for passenger service.
Station platforms at both approaches will welcome passengers onto the rail link that finally connects Jammu to the Kashmir Valley.
The permanent maintenance facility commissions with equipment for a century of bridge stewardship.
The final cable crane tower section descends. Construction infrastructure that lifted 30,000 tons. 20 years of construction, dust clears from the deck surface. The bridge prepared for official inauguration and the first scheduled passenger service. Over 200 workers who built the bridge assemble at mid-span, representing the thousands who worked over 20 years to complete this crossing.
Special inspection coaches with panoramic windows positioned for the inaugural crossing, carrying officials who will witness the culmination.
The inaugural train departs Kauri station, carrying the first official crossing 306 meters above the river toward the Kashmir Valley.
The inaugural train crosses 306 meters above the Chenab River, passengers witnessing the view that 20 years of engineering made possible.
The first scheduled passenger service departs, beginning daily crossings that will connect communities separated. 1 week of operations, passenger services, freight movements, maintenance cycles. The bridge now absorbed into the daily rhythm of the railway network. Winter operations continue through Himalayan snowfall area. Anti-icing systems and heated track maintaining service when roads close for months.
Passengers experience the crossing 360 meters above the river, the view across the Himalayan peaks that justified 20 years of engineering.
467 meters of arch span, 28,000 tons of steel, 306,000 bolts.
20 years, 2,000 workers at peak construction. Multiple nations contributing expertise. Beyond the statistics, 131 meters of steel pier rising to carry passengers 360 meters above the river they couldn't cross before. Every 2 weeks, maintenance crews verify the systems that keep the bridge operational. Stewardship that must continue for the next 100 years.
20 years, 28,000 tons of steel, 66,000 cubic meters of concrete mutton, from empty gorge to the world's highest railway bridge.
The extraordinary becomes routine. Daily trains crossing the world's highest railway bridge.
306,000 bolts torqued to specification. Every weld inspected, every surface protected. Craftsmanship at the millimeter scale.
4 million worker hours across 20 years. Engineering from 4 continents.
The Chenab Rail Bridge, 467 meters of arch, 359 meters above the river, the highest railway bridge on earth.
Where the Himalayas said impossible quain, engineering answered with steel, concrete, and 20 years of human determination.
Before they were icons, they were being built. Subscribe to Industrial Evolution.